Right. The final talk for the session is from SMT to ASP, solver-based approaches to solving Datalog synthesis as rule selection problems. The speaker here is Bembenek. Yes, the floor is yours.
Great, thank you. So this is joint work with Michael and Steve. And essentially, I'm going to be showing how we can use this really cool constraint solving technology from the AI community to solve a Datalog synthesis problem that PL researchers have been working on. Not only to solve it, but to solve it like very effectively and very simply. But before I get there, let me give a little bit of background. See if this works. Guess not. Okay. All right. So the language we're synthesizing is Datalog. A Datalog computation consists of two main parts. We first have a set of facts, such as the edges in a graph. This is the input to the program. We then have a set of inference rules that can be used for deriving new facts. For example, these rules compute graph transitive closure. And this is the rules are really like the core of the program itself. So when we want to run a Datalog computation, we stick these two things together and compute their least fixed point. In this case, our initial facts will be part of it, as will facts we can derive using our first rule, and then facts we can derive using our second rule. And this is it. This is all the facts we can derive, so we're done. We've reached the fixed point. It's also equivalently a least model. So if we interpret the rules as being these logical implications where the variables are universally quantified, that's another interpretation. And this model theoretic view will be helpful to keep in mind for later. So this is Datalog in a nutshell. It's very simple little language, but it actually has a lot of applications across like broad domains, and it's also used by some companies. So it's not a purely academic thing, despite its simplicity. So we're talking about Datalog synthesis, and in particular, we're going to be building on a line of work that started in 2018. And this approach to Datalog synthesis consists of two parts. So in step one, generate a set of candidate Datalog rules. And step two is filtering that set to find a subset that fits some input-output example. For instance, say we want to synthesize graph transitive closure, everybody's favorite Datalog program. Maybe we generate these candidate rules here. We have some input graph, some expected output. And then given this input and output, we can say we need to reject the first rule and accept the second two ones. This second phase of the problem, the rule selection, has become known as synthesis as rule selection, and it's sort of been studied as a problem in its own. So there's been a line of work using different techniques trying to solve this second part. And our work is sort of the next step in this progression. In particular, we make 4 contributions. So the first is we've developed this progression of algorithms for solving this problem. We've evaluated them. We've actually, in the paper, we offer some critiques of the problem and some ways to maybe generalize it. And then finally, and I think this is the point that we're probably most excited about, is that we demonstrate that this sort of interesting AI-based technology called answer set programming is able to really effectively solve this problem that people in the PL community have been working on. And to see what that looks like in pictures, here is, without going into the details, here are some performance numbers from running different synthesis tools on the benchmark suite. And here are the ASP-based solutions. So as you can see, they just totally crush it here. Like they basically take no time at all on this benchmark suite. And what this tells us is that ASP is a very powerful technology that can solve problems that PL people might care about. And because of this, we should really consider making ASP part of the PL practitioner's toolbox, along with more common technologies, more familiar ones at least, like SAT and SMT. So because of time limitations, I can't talk about everything, obviously. So I'll just hit on points 1 and 4. The talk is just going to proceed by going through this progression of algorithms we've developed, culminating in the use of ASP. So we start with ProSynth, which is the prior state-of-the-art algorithm. And this was actually published at POPL just a couple years ago. And it's based on the idea of counterexample-guided inductive synthesis using Datalog provenance. So throughout this talk, there'll be a series of diagrams. They're all going to use this shared vocabulary here, where we use different colors to differentiate between SAT-like and Datalog-like computation, and also different lines to indicate different types of interactions between components. So for ProSynth, we have a SAT solver that's going to be talking to some checking logic. And the checking logic is going to receive the input-output example and eventually produce some row selection. The way that happens is that the SAT solver guesses a row selection. The checking logic either accepts it or rejects it and passes on some blocking constraints to force the SAT solver to produce a new row selection. How does it do this? Well, on the side, we have our candidate rules, which have been compiled into a Datalog program. And essentially, we test the row selection on that input, see what we get. And from that, we extract Datalog provenance, which tells us why a fact was able to be derived or why we were unable to derive a fact. Using this provenance, ProSynth is able to construct the blocking constraints to pass back to the SAT solver. So this is ProSynth in a nutshell. Our first tool is called Monosynth, and it builds right on top of ProSynth using an idea of monotonic SMT theories. The big disadvantage with ProSynth is that there's this very loose integration between the SAT solving part and the Datalog part. So from an engineering perspective, they're different operating system processes, but from a deeper algorithmic perspective, there's no way for the checking logic to ever proactively prune a bad partial row selection that the SAT solver is coming up with. So the SAT solver always produces a complete row selection. Monosynth is going to fix these shortcomings. And it's going to do it by introducing this SMT theory of Datalog. So take your favorite DPLT-based SMT solver. It's going to have some SAT solver core in it that's going to communicate with theory-specific solvers. Here, we're going to have a theory of Datalog. The SAT solver will produce a partial row selection. A theory of Datalog will return conflicts if it doesn't like that row selection. How is it going to do that? Well, in a way that's very similar to ProSynth, we'll have our Datalog program on the side. We're going to basically test that row selection on it, get back provenance, and use that to construct conflicts if that's not a good row selection. So this part here, constructing conflicts from provenance, we're doing exactly what ProSynth is doing. The big difference is that we're actually doing this on a partial row selection instead of a complete row selection. And how are we able to do that? We can do that. The intuition is that the set of facts we can derive grows monotonically with the set of rules in our candidate rule set. So if we have a partial row selection, if we can derive some fact under that partial row selection, we know, and that fact is undesirable, then we know that we can prune every extension of that partial row selection. The technical result here is that every Datalog program could be the basis of a monotonic SMT theory. So this is a class of SMT theories that are especially efficient. And we've actually implemented this. So we've extended Z3 and CBC4 so that you can basically take your favorite Datalog program and plug it in, and you get a custom monotonic theory out of it. OK, so returning to Monosynth, this is the core. We sort of stick it inside a single process. We have some encoding logic that takes the input-output example, turns it into SMT assertions, gets back a model, and then from that model extracts the row selection. This leads to some speedups over ProSynth. The magnitude sort of depends whether you use Z3 or CBC4 as the backend solver. All right, so that's Monosynth in a nutshell. Our next tool is called LoopSynth, and this combines SAT solving and loop formulas. The big disadvantage with Monosynth is that the SAT solver is making very uneducated guesses. And in particular, it never actually sees the candidate rules. So what LoopSynth is going to do is actually try to encode those candidate rules as SAT formulas. Turns out that this is actually a little bit trickier than you might think. And so once again, to reiterate here, the idea is that we come up with a SAT encoding that the model is going to give us the row selection. So say we have this little synthesis problem. We have two candidate rules, some input Q and expected output P. It has to be that any valid row selection, given the specification, needs to include row 0, because rule 1, from a Datalog perspective, is a no-op. Doesn't do anything. So let's look at a potential encoding. So here's a very simple, naive encoding. We just take our candidate rules, turn them into logical implications, and we tack on an atom that identifies that rule. And then we state our specification. So unsurprisingly, this doesn't work. Why not? Well, because the set P and Q is a model, and essentially the solver can just assume that P is true without being forced to pick a rule that actually derives it. Fortunately, this is pretty easy to fix. We use something called the Clark completion, where we just take the bodies of the rules, turn them into a disjunction, and then set that equal to what we're deriving in that rule. So this solves the first problem. P and Q is no longer a model. Great. But we have another problem. The problem is that the set P, Q, and rule 1 is a model. And this is despite the fact that we said that any valid row selection needs to include rule 0 in it. And so what's going on here? What's the problem? Well, fundamentally, the problem is that SAT is trying to find any model, but Datalog needs a least model. So there's a basic disconnect that seems to be happening here. The way to get around this, or at least the way we get around it, is by taking advantage of some existing work. It's called the answer set SAT algorithm, or ASSAT for short. And this algorithm was originally introduced for computing answer sets, which I'll talk about very soon. But we're going to repurpose it for our synthesis problem. So the basic idea is we're going to encode the Clark completion of the ground program, which is a version of the program where we've replaced all variables with constants. And then we enter a loop. So we loop until the SAT solver gives us a least model. And in each iteration of the loop, we add a loop formula that rules out models that aren't least models. I'm not going to say kind of like the details of what these loop formulas are, but essentially they correspond to self-reinforcing cycles of ground atoms. So like we saw with rule 1 on the prior slide. And because of this, there may be exponentially many of them. In practice, there are often fewer. Our tool loopsynth uses this ASSAT algorithm essentially to solve the Datalog synthesis. I know there's a lot going on here, so I'm just going to highlight two things. The first is, as promised, we are actually taking our ground rules and encoding them into the SAT solver. And the second is that the checking logic is now returning these loop formulas. So before it was constructing conflicts using Datalog provenance, it's no longer doing that at all. It's just using these loop formulas. So these two things, the fact that we're encoding the rules themselves and that we're using these loop formulas to guide the SAT solver, is really what differentiate this approach from prior ones. So this achieves some speed up in the case of using CBC4, but it's actually a little slower in the case of using Z3 as the backend solver, which is a little sad, but it's okay because we're on the right track, I promise. Our final tool is called ASP Synth, and it uses off-the-shelf ASP solving. The basic idea here is that we want to encode our problem as an answer set program, and then we'll solve it using just a off-the-shelf solver. So I've mentioned ASP a bunch of times without telling you what it is, but it's a non-monotonic constraint solving paradigm that's actually a superset of Datalog. So in the Datalog fragment, the semantics correspond. So if we have this really simple little program, P of P, there's a single answer set, which is the empty model, and this is what we'd expect for Datalog as well. However, ASP can also contemplate programs that Datalog can't, such as those using sort of arbitrary negation. So this program, P if not Q, Q if not P. Under the answer set semantics, this has two possible solutions. either the singleton model P or the singleton model Q. And what's happening is that essentially the solver is allowed to choose which of these, whether P or Q, should be in the answer set. And this is really where the power of answer set programming comes in. It's the ability to make choices while still being consistent in some respect with Datalog. So there are two main flavors of ASP solving. One we've seen already, which is translating to SAT. And then there are also these native custom solvers, which use SAT-like techniques, but don't actually use a SAT backend. And we'll take advantage of the fact that these can be very efficient and highly engineered. So we have show an ASP encoding of row selection. So this encoding will give us the row selection, the model. So we can take our candidate rules and just encode them in a very straightforward way. We'll state them, tack on an atom identifying each rule. And then we'll also add these choice rules. So these are some syntactic sugar, but essentially it means the ASP solver is allowed to choose whether or not that atom is part of the answer set. So the ASP solver here is going to be very explicitly choosing which rules to include. Our input, we can just copy over. Our output, we'll use a layer of indirection saying that just sort of enumerating what we expect, and then adding some hard constraints that make sure that we only derive things that we expect to derive. So the first constraint says it shouldn't be the case that we expect to derive something and we fail to derive it. And the other rule says it shouldn't be the case that we derive something that we don't expect. I'll just give you a few more seconds to look this over. Okay. So ASP Synth is our tool that uses this encoding. As you can see, this diagram is a lot simpler than the other ones. Why is that? Well, one thing you'll notice is that there's absolutely no repeat interactions happening here. And why is that? Well, it's because our ASP solver is combining in a single procedure stuff that had to be separate before, essentially the SAT-like search along with the Hornclaw solving. And it's this combination, the fact that the ASP solver can do this for us, that gives us a very simple solution and also a very effective one. So this one has like a 9x geometric mean speedup over prosynth. And it's also easy to tweak it to do stuff like find minimal minimal solutions. So in conclusion, I've shown this progression of 3 algorithms for solving this Datalog synthesis problem. And we've also demonstrated that this AI technology, ASP, is able to very effectively solve this problem of interest to PL folks. And I hope this gets you thinking, like maybe ASP can help me solve my PL problem. And in particular, I would encourage people who are interested to check out work from the inductive logic programming community. These are essentially AI people who work on logic programming synthesis and who have developed tools that are use ASP in much more sophisticated ways than what I've shown here. There's a lot more in the paper, including all the details about the stuff I've sort of omitted here. And with that, I'll just say thank you.
All right. Have we got questions from the crowd? Yep.
Hello, Leonard Beringer from Princeton. Did I understand it right that ASP not only has the finds different models, but also operates over an extended syntax, like with negation on the right-hand side?
Yeah, so it has
so does that mean that there is, in principle, also the problem of ASP rule synthesis? Mm-hmm. And would your approach apply to that as well? Mm-hmm.
Our approach, the encoding we use is sort of like a simplified version of an encoding that some ASP synthesis tools also use. So yeah, definitely.
Hi, Michael Arntinius from Relational AI. So you have to like ground all the variables. Doesn't this produce a combinatorial explosion? Does this limit the size of the problems you can tackle?
Yeah, so Haven't talked about it specifically, but on loop synth, we can kind of see this happening, or actually with ASP synth as well, sorry. I'll just go here. But essentially, so the way that ASP solvers work is typically they have this grounding phase before a solving phase. As you can see, the grounder passes stuff to the ASP solver. And this, in practice, can be one of the big bottlenecks for ASP solving. So in the benchmark suite we were operating on, the problems are pretty small, so it wasn't a problem. We do also have results on like a scalability experiment where we saw essentially our approach scaled pretty well if you just change either like the size of the input-output example or the size of the candidate rule set. But if you made them both bigger, then our approach ended up being slower than some approaches where you actually just like generate the rules instead of having a pre-selected set. Yeah.
Thank you.
Hi, I'm David Zell from Relational AI. So one of the limitations of ProSynth was that you couldn't synthesize Datalog programs with negation. Does your ASP-based approach allow that?
Yeah, so the way we would do that, so like if you, for example, if you wanted to synthesize programs that has stratified negation, essentially you would have your candidate rule set and some rules would have negation in it. And then you would essentially add some new constraints to your encoding that enforce stratification in the final rule selection. So I think that would be a relatively easy extension of this.
Thanks.
Do we have any more questions?
Hi, my name is Langston, and I work at Gawa. So you said that your approach doesn't scale as well as some other approaches that don't have a pre-selected list of rules that you're selecting from.
Yeah.
Is that part of your critique of this framing of the problem?
Yeah, so I think overall, like, it's not clear exactly what the right like use case, like what the real world scenario that this like problem framing fits into. And so that's something we'd like to explore in future work. Like maybe there are some cases where you have an existing Datalog program, it's not quite right. Maybe you can mutate the rules a little bit and then choose among them. So that's like a potential. But yeah, so there's kind of, one of our critiques does have to do with this assumption about like starting off with a rule set. Yeah.
Well, if there's no more questions, let's thank the speaker again.
Thank you.